We're okay. So welcome everyone to the first One World Probability seminar for the semester. We're very pleased to have our first speakers, Martin Heyer and Shen. Martin Heyer will be speaking to us about stochastic quantization of Yang-Mills. So just to let you know, there will be a question session at the end, but if you have questions during the talk, feel free to raise your hand or drop it into the chat. Okay, thank you very much. Over to you, Martin.
Okay, thanks a lot, and thanks for the invite. I still had a weird echo, so I have to try to ignore that. So I'm going to talk about stochastic quantization of Yang-Mills. And this is sorry, this is really annoying. I can't turn off the audio for the iPad, and so I get. Let me just try to turn it off inside Zoom. Does anybody know how to turn off audio completely for Zoom?
Are you able to mute your iPad, perhaps?
I think no. I tried that, but now it's fine. Okay.
Okay.
I'm good. Okay. Sorry. Right. Okay. So as Ilya mentioned, I'm going to talk about stochastic quantization of Yang-Mills, and so this is joint work with AJ Chandra from Imperial, well, Ilya himself. And Shen, who's going to give the second lecture in this One World Probability seminar. And I wouldn't necessarily assume that any of you knows what the words in the title mean. So I'm going to basically try to explain what stochastic quantization is about, and then I'm going to explain what Yang-Mills theory is about. And then we're going to kind of get to the statement of the results, and presumably that's then pretty much going to be the end of the lecture. So the main point is going to get you to actually understand what we proved, and what was the motivation for these results. So the stochastic quantization business. The context here is the context of Euclidean quantum field theory. And so it relates to real quantum field theory, but I don't want to explain the way in which it relates. So that's an old story that goes back to the 60s, to the works of Osterwalder and Schrader. And the basic construction here is that you take a functional on a space of fields. So the example, right, the running example that you should have in mind is something like S of phi equal to, say, a half integral of gradient phi square, right? So that would be the simplest example, where phi would be a scalar field, so just a function from your state space, which is maybe the torus, into the reals. And then what you're trying to do in Euclidean quantum field theory is you try to give a meaning to a probability measure, which at least formally would be proportional to, well, there's maybe a proportionality constant, right? You would put sort of a partition function here. So probability measure, which is proportional to e to the minus this action functional times Lebesgue measure on the space of fields, right? And of course, this is obviously completely formal because there's no Lebesgue measure in any kind of infinite dimensional space. But if the action functional S grows sufficiently fast in all directions, you might hope that still there's some way of taking approximations and passing to the limit to actually get a well-defined probability measure, right? So in the particular example, I think the example I gave you here, S is quadratic, and so you would think that, well, e to the minus some bilinear functional of your state that should define a Gaussian measure. And in this particular case, you can guess what should be the covariance of that measure, right? Because the the density of a Gaussian measure with covariance C would be e to the minus a half. It would be like e to, let me write it down, so of e to the minus a half x of C inverse x dx, right? That will be a Gaussian measure with covariance C. And so if we compare this to this expression up here, we see that, well, this I could write it as a half of the L2 scalar product of phi with Laplacian phi, well, minus, I guess. And so if I compare these expressions, you see that the covariance here should be the inverse of the Laplacian. So it should be the Green's function of the Laplacian. And that's what's called the Gaussian free field, which is precisely the Gaussian measure that formally you would write as e to the minus this Dirichlet energy. Okay. Now, of course, in one dimension, that would just give you Brownian motion, right? At least formally. Now, of course, these sort of expressions, they show up a lot in statistical mechanics, right? Where this functional would be something like an energy functional. But the motivation for the work that I'm going to talk about today, that really comes more from quantum field theory. So the energy functional that we're going to take is what's called the Young-Mills functional. And as far as I know, there isn't really much of a statistical mechanics interpretation of the Young-Mills functional. So it's really sort of motivated by quantum mechanics. So now what's the Young-Mills functional? So in this case, so in the case of Young-Mills, the space of fields, right, which in the case of the free field, your fields were really just scalar fields, so like functions from, say, the torus into the reals. So in the case of Young-Mills, you start with a compact Lie group. So the kind of example that you should have in mind is, I would always, in terms of formulas, I would always basically assume that elements of G are matrices, right? And you can just assume that G is something like, n times n orthogonal matrices, for example, right? So SON is a perfectly nice example of a G to have in mind. And we write this Gothic G for the Lie algebra of G. And now our fields, instead of being scalar valued functions, they are actually G valued one forms on, whatever space you're considering. So I'm always going to consider the torus as my space. And so in reality, the picture one should have in mind, right, is that there's the actual physical space, which is some torus, TD. And then at every point of the torus, you kind of attach a copy of G. So let me draw it, like this is a copy of G. Except that the way you should really think about it is that, we sort of forget about which element of G is the identity element. So we really want to consider this modulo reparametrizations, where reparametrization would really correspond to, at every point, multiplying elements in that copy of G by some element of G that might depend on the point, right? So if your G is a circle, so that would be the simplest case of U1, which is not a terribly interesting Lie group because it's abelian, but as far as pictures are concerned, it's the easiest one to draw. So imagine we have our torus, we have a circle attached at every point of the torus. And now we want to view this picture modulo rotations, where you're allowed to rotate at every point, you're allowed to rotate the circle by some amount, and the amount could depend on the point, right? And now, is there a question? I think I heard some. No. Okay, so, and now these fields A, the way one should interpret them is as connections. And so what it really means is that they provide a notion of horizontal lift on this space, in the sense that if you give yourself a curve, so let me draw it, say, in red, you take a curve So that's a curve which lives downstairs on the torus. And then, you know, at every point you have this copy of G. Now what you want to do is you want to lift this curve to a curve on your space, so that at every point, at every instant of time, my curve somehow, you know, at time t lives in the copy of G that sits above the point, the corresponding point for the original curve, right? So you get a notion of lift of these curves from a curve on the torus into a curve on the torus times G. And now what you have to specify is at every point in which direction, you know, inside G, in which direction you're moving. And that's exactly what A tells you, right? Because the one form, what does it do? You feed it a tangent vector of the torus, which would be the direction in which you're moving, in which the red curve is moving downstairs. And it spits out an element of the Lie algebra, which is really an element of the tangent space of the Lie group. And so it tells you, you know, your lifted curve. Well, as far as the projection on the torus is concerned, you know that it has to move exactly like the original curve. And so the only thing, extra ingredient you need to specify is in which direction it moves inside the group, right? And that's precisely what A tells you, right? You feed it the derivative of your curve, that's a tangent vector of the torus, and it spits out an element of the Lie algebra, which is an element of the tangent vector of G. Okay, and so that gives you a notion of kind of horizontal lift. And now, whenever you have such a notion of such a connection in, you know, quite large generality, whenever there's a notion of connection, there's an associated notion of curvature. And in the case of, so for example, in the case of Riemannian geometry, there's maybe the usual notion of connection that you know, which basically allows you to move tangent vectors around. So in this case, like the space that lives above a point is the tangent space, and your connection allows you to lift somehow curves in the original space into curves on the tangent bundle by kind of moving back tangent vectors around. And then there's a notion of curvature that goes with it, which would just be the Riemannian curvature tensor. In this particular case, the associated curvature tensor is a two form with values in G, and in coordinates it's given by this expression here. And the way you should think of the curvature is basically to say, well, you look at the lift, you take a small loop in your torus, and now the loop, in order to specify a loop, basically you have to say in which plane it lies. So you have to give two tangent vectors, right? So that specifies a little loop or a little ellipsoid if you want. And then you run around the little ellipsoid or little parallelogram, and you lift it, and downstairs on the torus, the little loop closes up. But when you lift it, it doesn't necessarily close up, right? There's no guarantee with a specification of such a form. You know, if you perform one of these horizontal lifts, there's no guarantee that the loop actually closes up upstairs in G. And you know, if you do the calculation, you see that up to first order, it closes up to order epsilon if the size of the loop is epsilon. But then, you know, there's a next order epsilon square to which it may not close up. And the curvature tensor is precisely the coefficient that you find in front of the epsilon square. Okay, so it's sort of the defect, it's some kind of integrability defect of your one form. And so then the Yang-Mills action is just the L2 norm of that curvature. Okay, so that's the definition of the Yang-Mills action. And you see that, you know, in terms of structure of this action functional, it's kind of similar to what we had for the free field, right? So remember, in the case of the free field, the action was just the integral of the gradient square. So here it's again an integral of some local functional squared. So local in the sense that f at x really only depends on a at x and maybe derivatives of a at x. Right? So this here is the Lie bracket in that Lie algebra. Right? Remember, these AIs are Lie algebra valued. So you have some local functional of which you take the L2 norm. And furthermore, that local functional basically involves first order derivatives. Right? So it's so that part looks very similar to the free field. And then there's an extra part here, which is quadratic in A, which then gives you kind of a quartic term. So that shows already that this e to the minus s certainly wouldn't be a Gaussian measure, right? If you can give a meaning to it. The big difference is that you have this Yang-Mills action functional has a huge symmetry group. And in fact, remember I mentioned at the very beginning that one should really think this torus times Lie group, one should think of that Lie group as being the Lie group where we have forgotten about which element is the identity element. If you want, the consequence of this is that all the constructions are going to be invariant under, you know, these changes of coordinates obtained by rotating each of the copies of G, you know, above every point of the torus. So you have this gauge group, which is just functions from the torus into G, right? So that will be your rotation at every point you specify by how much you rotate things. And that's a group, right? I mean, if I have a function G1 and a function G2, G1 times G2 of x is just G1 of x times G2 of x, right? So it's just pointwise multiplication. That makes it a very big group. It's, as a group, it's not terribly interesting because it's in some sense just some sort of a big product. But this group actually acts, so it has a natural action in the sense that, you know, you can ask yourself, if I perform that rotation above every point, and then I do again my horizontal lift, how should I transform this one form G, so this one form A, so how should I transform that connection in such a way that the horizontal lift is the same, right? So that like the that first rotating and then performing the horizontal lift is the same as first performing the horizontal lift and then rotating. Right? So what is the correct way of modifying A so that, you know, this diagram kind of commutes if you want? And if you do the calculation, what you find is something like this, so that A actually doesn't get, so in some sense, the simple guess would have been that A gets transformed by simply conjugation with G. And that's actually in a way how genuine one forms should transform under the action of this gauge group. But A is not really a one form, it's really it has this geometric interpretation of the connection. And the situation here is very similar to the situation in Riemannian geometry, where a connection, if you remember from, you know, whatever course on Riemannian geometry you've taken, a connection is described by its Christoffel symbols, and they are a function with 3 indices. So it's a little bit like a tensor with 3 indices, but it doesn't exactly transform like a tensor. Right? So Christoffel symbols transform in a certain way under changes of coordinates, which is not the same as a tensor with the same number of indices. And it's the same story here. So this connection on this space looks like a one form in the sense that it has one index, takes values in G, but it doesn't transform exactly like one forms, it transforms a little bit differently. There's this additional term here. And so that's the way how connections transform under these type of changes of coordinates. And what one finds is that if, at least if the norm, right, so here I didn't quite specify which norm I mean here. Remember, this guy takes values in the Lie algebra, so I have to choose a norm in the Lie algebra. And the norm in the Lie algebra here is always going to be chosen in such a way that the norm of an element H is equal to the norm of the conjugation of H with any element of the group G. So if you think of it as matrices, you can always, if you have a compact Lie group, you can always realize it as orthogonal matrices. And then, you take the norm under which the matrices are orthogonal, so they preserve the norm. Okay, so that's the natural norm, if you want, on the group G. And so if you choose that norm, then this guy really transforms in the correct way, in the sense that the curvature associated to AG is just the curvature associated to A conjugated with G. But then this norm is invariant under conjugation, and therefore S is invariant under the action of that group. Right. So when I mean invariant, it means that S of AG is equal to S of A for every G in this big group curly G. Right. So you have this very big symmetry group for the action, which basically means that the action functional is very flat in many directions. Right? That's kind of what this means. So that's a problem for defining our measure. Right? So remember that what we want to do is we would want to give a meaning to the measure e to the minus s of a dA, where dA is something like Lebesgue measure. Right? But now if S is flat in infinitely many directions, that basically means that there's infinitely many directions in which it kind of looks, in which this measure should look like Lebesgue measure. Okay, and that's again a problem because we all know that there's no Lebesgue measure in infinite dimensions. Right? So that kind of hints at the fact that there's no chance of building such a measure. Now, the good news is that, again, we only care about things modulo the action of this gauge group, right? And so in particular, all the physical observables, you should think of the physical observables, so that's maps from the space of connections into the real numbers, say. All the physical observables we care about are gauge invariant, right? So in the same sense as before, so that the observable acted upon A to the G, so if the transformed A is the same as the observable acted on A, and that should be true for every element of the gauge group. Right? So an example of such a physical observable is what's called a Wilson loop, which is basically exactly what I was describing before. Right? You take a loop on the torus, you lift it on torus times group, and then in general, the loop doesn't close up. So you look by how much it doesn't close up, which is this quantity here, and then you take the trace, or you take any other class function, right? So a class function is a function on the group which is invariant under conjugation. Simplest example of a class function, if you have a matrix group, is just the trace. Okay, so you should think of this here, you should think of it as being the trace. So that would be an example of physical observable. Right? And so since we only care about physical observables, what it really means is that we don't really care about building that measure on all connections, on the space of all connections, but we really just care about it on the space of gauge orbit. So gauge orbit is just the orbit of a connection under the action of the gauge group, right? So this would be the space of orbits, right? So it's like connections quotiented by gauge group. Okay. So then you have a chance, at least this objection we had here. So this objection is no longer much of an objection because now the infinitely many directions in which the action functional is flat, they just collapse to a point, right? So we don't need to build the bed measure on these directions. Well, still, that doesn't really help at building the measure. It just somehow, it's an argument about saying that it's not completely implausible that such a measure exists in some sense, right? But it still doesn't actually allow us to build it. Now, okay, so let me give sort of mention a few somehow previous results. So in 2 dimensions, and that's an important fact, and you're going to hear much more about the 2-dimensional case in House Talk in half an hour. In 2 dimensions, you actually can guess. So some time ago already, basically physicists guessed the joint law of these Wilson loop observables under the Yang-Mills measure. Right? So if you can build this Yang-Mills measure, so e to the minus Yang-Mills action functional times Lebesgue, you normalize it, so it's a probability measure. So then you can draw a random action from it, a random connection from that measure, right? So it gives you a notion of random connection. And then you can take any of the observables, like these Wilson loop observables. And so now these become just random variables, right? And so you can take k different loops and then ask yourself, what's the joint law of these k random variables under this Yang-Mills measure? And in 2 dimensions, you can actually guess that joint law, okay? And so in some sense, one has a description of this Yang-Mills measure, at least in terms of somehow k point distributions, right? So it's a little bit like, you know, you can view a stochastic process as a collection of k point distributions by just knowing the joint distribution of the process at any k number of times, right? That's not quite the same as, you know, constructing the process, for example, as a probability measure on a space of continuous functions, right? So it gives you much less topological information if you want. But on the other hand, it's enough information typically to completely characterize the process, right? And here, well, these Wilson loop observables, it turns out that they are sufficiently rich to actually characterize elements of that quotient space. Okay, so in principle, if you know the joint laws of all possible Wilson loop observables, these, okay, modulo a little bit of technicalities, that basically characterizes your probability measure, okay? So in 2 dimensions, in some sense, the measure is known in that sense, right? In 3 dimensions, that's not the case. And so there is some previous work, in particular, there's a series of works by Balaban from the 80s, where they argue that in some sense, if you approximate, there are some sort of discrete, it's dimension of the torus here, right? So the dimension of G is to some extent irrelevant for these constructions. Okay. So in 3 dimensions, there are some arguments by Balaban and others that at least in some sense, there is some notion of, you know, you take some kind of discrete approximation of these measures and there's some type of stability as you try to remove, as you try to send the lattice spacing to 0, but it doesn't actually construct really a limiting probability measure on any kind of state space. There's a whole series of other results that take a sort of orthogonal direction. So instead of trying to build a measure on the continuum, you stay in the discrete space, but you look at limits where the dimension of the group goes to infinity, right? So you look at ON with n very large, and then again, there's some other simplifications that happen, but that goes off into a completely different direction. So I'm not going to say anything more about that. So now let me talk a bit about stochastic quantization, right? So remember the first half of the title was stochastic quantization, which is a notion that was proposed by Parisi and Wu in 81. And the idea is, just the thing that you're all familiar with, which is that if you have a, say on Rn, in finite dimension, so if I take for phi here now just a element of Rn rather than an element of some space of connections or something like that, and you have a measure of the form e to the minus some functional times Lebesgue measure, then that measure is invariant for noisy gradient flow, right? So if you just take gradient descent and you add white noise, then that's a Langevin, kind of the Langevin diffusion that's associated to this measure, and we all know that this measure is invariant for that diffusion if S is nice and it kind of grows in all directions sufficiently fast, right? And so then the hope is that, well, maybe you can actually build this dynamic, right? Instead of building the Yang-Mills measure, why not actually build the dynamic and then just define the measure as being the invariant measure for that dynamic? Okay. So if you do that for Yang-Mills, you just compute, if you want, okay, so for a notion of gradient, you need a metric. So say you take the L2 metric, which is the natural metric here. So if you take the L2 gradient of the Yang-Mills functional, and then you add white noise, then you get this equation here. So that's okay. So you get some equation like this, where this dA here is some kind of it's a slightly twisted exterior derivative. Okay? And star here really just means the L2 adjoint. Okay? And so one thing you say, and psi here denotes space-time white noise. Right? And why should it be white in space? Well, that's basically because the covariance structure of the noise needs to be compatible with the metric that you choose for your choice of gradient. Right? So if you take an L2 gradient, then it means that the Cameron-Martin space of your noise should be L2, and the noise with Cameron-Martin space L2 is white noise, okay? White in space. Now, a problem you can see with this equation is that it's not parabolic, because here you have something that looks a bit like a Laplacian, right? It's a d star d. But actually, if you remember in differential geometry, the Laplacian on K forms is not d star d, but it's d star d plus dd star. And unless you're on sort of, either 1 forms or d forms, I guess, this operator here is not elliptic. Okay, it's only half of a Laplacian if you want. And so actually, if you write it in coordinates, it looks like this. Right? It's sort of a Laplacian, but then there's this extra off-diagonal term, which makes it non-elliptic. Okay, and then there are these lower order terms. When I write lower order, I mean in terms of number of derivatives. So these are the only terms that have 2 derivatives in space. And all the other terms, they might have higher powers of A, but less derivatives. So they have either 1 derivative or no derivative. But then there's a trick here, which is originally due to de Turk in a different context, in the context of Ricci flow, and to Donaldson in the context of Yang-Mills, which is to basically say, well, if you, so here's the picture. So if you, remember, we only care about the dynamic modulo the action of the gauge group. Right, so so the picture here, you should think of these lines as being the orbits of points under the action of the gauge group, right? So here a point is a connection, so that's your state space for your evolution. And here would be some connection A, and here's the image of A under the action of the gauge group. And now we only care about the evolution modulo that action, right? So this point and this point, we consider them as being equal, right? So we want only to build an evolution in the quotient space. And what it means is that we don't care about motion in this direction, right? So we can change the evolution and add some additional motion that goes in the direction of the orbits. And as far as we're concerned, since at the end of the day, we only care about the evolution in the quotient space, that shouldn't change it, right? And so it turns out you can add, so what it means, move in the direction of the gauge orbits. It turns out that it's adding any term of the form this twisted exterior derivative that already showed up on the previous slide, applied to anything, basically any zero form that might depend in any way that you want on the connection A. And so one natural way, right, A is a one form, a natural way to get a zero form out of a one form is to take the adjoint of the exterior derivative, right? And then that gives you a dd star term. So remember the equation was of the form d star d of A plus stuff. And now we're basically told that, well, we can add a term which is of the form dd star of A, and we can just add it for free. Okay? That doesn't really change about the parts of the dynamic that we care about. And so in that way, we can remove this term. We can basically turn this dd star, the d star d that we had, into an actual Laplacian, into a d star d plus dd star. Right? And then the equation is at least elliptic, which is already a good start, right? So if we do this, the equation that we end up with has the following structure, right? So it has this structure here. You write it out in coordinates. There's a heat equation part. Then there's a bilinear form in A and its spatial derivatives, first order spatial derivatives. And then there's some trilinear form in A. And then there's space-time white noise, okay? Now, okay, so it's a parabolic stochastic PDE. The problem that you still have is that even if you ignore the nonlinear parts, the solution to, if you just take the heat equation with white noise, the solutions to that equation would look like a free field at fixed time, right? And the free field already in dimension 2, its distribution value. Right? And it's in dimension 2, it's so just about the distribution, so it has kind of regularity 0 in some sense. And then in dimension 3, it has half less, so regularity minus a half, and so on. And so, you know, these terms are both clearly problematic, right? Especially in dimension 3. So you're trying to take the cube of something that has regularity minus a half, or multiplying a guy of regularity minus a half with something of regularity minus 3 halves, right? So these are extremely singular operations. But that's, so fortunately by now, so we have this general theory of regularity structures that allows us to give meaning to equations of that type, okay? And so I'm not going to go into details of how the theory works. I just take it as a black box and sort of explain what it says. So in this particular context, what it says is that if you smoothen out the noise, so if you replace the noise by some epsilon noise, so say it's, instead of having delta function as correlations in space and time, it has approximate delta functions as correlations, right? So you take an epsilon approximation of a delta function, so then it's actually smooth. So then the equation is perfectly meaningful. And then you would like to send epsilon to 0, right? And what the theory says is that, well, if you just do that and you just send epsilon to 0, then in general, there's no reason why it should converge, why solutions should converge. But you can, at least in dimensions strictly less than 4, for equations of this particular structure, you can add a counter term to the equation. So you can modify the equation in some kind of minimal way, in such a way that the solutions to the modified equation converge as epsilon goes to 0. Okay, so in this particular case, what the theory tells you is that you have to add a term of this type. So you have to add a counter term which is just linear in A, and with some constant in front. So this here is a multiple of the identity. And this constant here potentially could blow up as epsilon goes to 0. So there's basically an explicit formula for it. It's sort of a complicated formula, so it's not necessarily easy to extract prefactors or stuff like that out of the formula, but it is explicit. And the theory tells you, well, if you take that particular choice of the constant, then the sequence of solutions to this equation here has a limit, at least locally in time. So it might, maybe it blows up in finite time because you have these nonlinear terms, but at least locally in time, there's a limit. And the limit is sort of unique in the sense that, you know, here I said you replace the noise by something which has correlations that are approximate delta functions. The limit doesn't depend on the choice of approximation to the delta function that you make. The constants here do depend on it, right? So the constants here depend on the choice of approximation for the noise, but the limit does not. Okay? And now the problem you have here is that this actually appears to break this gauge invariance. So remember, the whole problem was kind of nicely invariant under the action of this gauge group. And so in particular, since we want to, at the end of the day, we would like to build a Markov process in this space of gauge orbits. And so one property we certainly want is that if we start with some initial condition A, and we compare it to the same process starting somewhere else on the same orbit, right? So if we look at the two solutions starting from these two initial conditions, then we would like the solutions to actually be the same modulo action of the gauge group, right? At least in law, because otherwise, otherwise the process that we build when we quotient out the action of the gauge group would no longer be a Markov process in general, right? So we would like to have this type of gauge invariance, and that's somehow a very rigid condition. So if you take this equation here and you just, close your eyes, pretend it has a meaning, ask yourself, if I act onto A with G, what's the new equation that you get? Then you can, do you actually get the same equation back? The answer is basically yes, but it relies on this very specific structure of this bilinear and this trilinear term. And it also relies very strongly on the noise here really being white noise, because what happens is that the noise ends up being conjugated with the element of the gauge group. And so you need conjugation with an arbitrary element of the gauge group to be a measure preserving transformation. And that's true for white noise, but it's no longer true if you color the noise, right? So it's true for white noise here, but it's no longer true for psi epsilon. So replacing white noise by some smoothened out colored noise breaks this gauge invariance, and replacing this equation here by this equation plus an extra term also breaks gauge invariance, okay? So we kind of break gauge invariance in two different ways here. And then the hope is that, well, maybe magically the two different ways of breaking gauge invariance actually cancel out, so that the whole thing is still gauge invariant in the limit as epsilon goes to 0. Okay? And another thing that one remarks here is that, I told you that there's basically an explicit formula for this constant C epsilon that appears here. But, I could add here a term of the type K times A epsilon. And this equation here also has a limit, right? The solutions to this equation also have a limit as epsilon goes to 0. And, as an equation, this equation here, whether I have this term or not, well, it's the same equation, right? It just changes the value of this constant by a little bit. So the theory here really gives me a one parameter family of solutions to this equation, which would be indexed by this finite part of the counter term, right? And then this gauge invariance property is sufficiently rigid that you can kind of convince yourself that if one member of this one parameter family is gauge invariant, then the others are probably not going to be, right? So you would expect that most one member of that family to actually be gauge invariant, right? So it's not clear if you just renormalize the equation, take the limit, there's actually no reason why you would get a gauge invariant limit, right? So you would have to be lucky to get the guy which is gauge invariant, but that a priori you don't even know if any of them is, right? And that's basically the main theorem. So the main theorem is that the magic happens, and there is indeed among that one parameter family, there is exactly one which is actually gauge invariant. And furthermore, what we show is some sense not just that that magic happens, so that would be 0.4 in this theorem, right? So that there's a unique way of choosing the constant, so that we get a Markov process even after taking the quotient by the action of the gauge group. The other thing we show is that you actually have a really nice state space. So you can find a nice state space on which this quotienting procedure is actually a nice procedure. So why is that? So first, why is it important and why is it non-trivial? The reason why it's non-trivial is that, well, you know, the space of connections in which you're working, clearly you cannot work with smooth connections, right? Because solutions, even in 2 dimensions, so this is the 2-dimensional result, even in 2 dimensions, they're going to look like a free field at fixed time, so they're not even functions. So you have to look at some kind of space of distributional connections. And then, okay, so you can act on them with smooth gauge transformations, right? So smooth functions from the torus into the gauge group, to the group G. But then taking the quotient space feels, if you want, a little bit like quotienting some space of distributions by a space of smooth functions under, say, addition, right? So say you take, for example, space of distributions of some fixed regularity over the interval 0, 1, and then you say that 2 distributions are equivalent if their difference is a smooth function. If you do that, the quotient space is horrible, right? So it's like, it's one of these spaces that are not even Borel spaces. So there's no, it basically has no non-constant measurable functions. It's not a space on which you want to do probability theory, right? So what you want to do is you would want to find a space of gauge transformation so that the quotient space is still a nice space. And the other thing you would like to do is you would like to, right, your space of connections needs to contain distributions, but on the other hand, you would kind of want to be able to integrate them along lines. And in general, you cannot restrict distributions on R2 onto a line, right, even if it's a smooth line. So what we do in 2 dimensions, we can actually introduce some notion of distributional one form, which can be integrated along lines. Okay? So we do actually really have, with these Wilson loop observables do actually make sense. They are continuous functions on our state space. And furthermore, the state space is such that, well, the action of how the continuous gauge transformation makes sense. So the G alpha here is just functions from the torus into G that are alpha Hölder continuous. And it's such that if you take the quotient space, it's actually a nice Polish space. So it has all the nice properties that you want as a probabilist, right? It's as nice as you want. So it's a perfectly nice state space for a Markov process. And so then you can show things like, you know, you get a process and the process is Feller. It's actually even strong fella, so it has kind of really nice properties, has continuous trajectories. So it's a really nice Markov process from the point of view of the theory of Markov processes, if you want. And furthermore, so one very recent result, which Hao is going to talk about in, I guess, 5 minutes, is that you can show that that process actually does have a unique invariant measure. And furthermore, the measure does coincide with the measure that the physicists had guessed back in, long time ago. In the sense that if you look at K-Wilson loops and you look at the joint distribution of K-Wilson loops under that measure, it is exactly the same as the K-loop distribution that had already appeared in the literature before. And then we have some partial results in 3 dimensions, but I think I'm kind of running out of time. Basically, the upshot is that this miracle about the renormalization counter term and the smoothing of the noise, that happens both in 2 and 3 dimensions. We don't have such a nice state space in 3 dimensions. So we have some sort of somewhat less complete results in the direction of constructing a nice state space for that process. But we still basically can build kind of a relatively nice Markov process that in 3 dimension has sort of the interpretation, if you want, as the natural Langevin dynamic for the 3-dimensional Yang-Mills measure, which is still, it doesn't quite. So we, unfortunately, we only have a local in time construction. So the big open question here is long time control of solutions, right? So if we knew that the solutions of our process exist for all times and we had uniform bounds, then we would have an invariant measure, and that would give a full construction of the Yang-Mills measure. So that's still work to do. And I think I stop here, and thank you very much for your attention.
Okay, thank you very much, Martin, for the very nice talk, even though it's quite late for you. Before the next talk, we have time for questions. So feel free to ask any questions or drop them into the chat. Okay. Could there be any special issues in D bigger than 3?
Oh yes, yeah. So that's a good question, right? So if I talked only about dimensions 2 and 3, that's because dimension 4 here is the critical dimension, in the sense that if you remember, the equation has a term, it looks like this, right? So there's a Laplacian term, then there's a term which is roughly like A times the derivative, then there's a cubic term, and then there's space-time white noise. Now, if you look at what is the regularity, or what is the scaling invariance property of these objects. So white noise scales like, well, in 1 dimension, it has scaling dimension -1/2, right? So if you rescale white noise, 1-dimensional white noise in time by a certain factor, you would have to rescale it by minus that factor to the power. You would have to rescale it vertically by kind of that factor to the power -1/2. It's the derivative of a Brownian motion. Brownian motion scales like +1/2. Now in D dimensions, white noise scales like -d+2/2 space-time white noise, where the d/2 is like regular white noise, right? Dimension 1 would be -1/2. And then the 2 corresponds to time, and the reason why it's an extra 2 and not an extra 1 is because of the parabolic scaling. Like 1 power of time is like 2 powers of space, right? Because of that balance here. Now that suggests that A should behave like 2 derivatives better, right? Because like a heat equation, you always gain 2. So this bumps you up from minus d plus 2 over 2 to 2 minus d over 2, right? So it's 2 better than the noise itself. And then what does it tell you about AQ, right? You see that that's still negative as soon as dimension is 2 or bigger, right? And now A cube, where it should scale basically like 3 times that. 2 minus 3 over 2. And now you can ask yourself, well, at which point does that guy become as singular as that guy, right? And that's exactly when minus d plus 2 is equal to 3 times 2 minus d. And that's exactly when d equal 4, right? When d equal 4 is here, you get minus 6, and here you get 3 times 2 minus 4, which is also minus 6, okay? And so in dimension 4, it starts to be the case that even at very small scales, the nonlinear terms can no longer be considered as perturbation, if you want, of the linear equation. And then this whole theory that I mentioned earlier breaks down, okay? And you really expect also to start different behavior, to start to see different behavior, right? Like, for example, for these 5-4 measure, which is like a simple cartoon for this, there's this recent result by Eisenman and Duminier-Copin, which showed that in 4 dimensions, the measure is actually trivial. But you try to build a non-trivial measure, and whatever you do, you can only get Gaussian measures somehow. So then there's how important is condition that you have a torus. Yeah, so that's okay. We think that we can probably do more general G bundles as long as things are compact. But it's technically a bit messy, and so we haven't written it up. The fact that the space is compact is really quite important. Right? So the fact that it's the torus should not be so important, but of course, in the proof, it does show up. It simplifies things a lot. The fact that it's compact is important. If it's not compact, then we don't even know how to get local solutions in time. And then what's the advantage instead of trying to construct directly the measure? Well, I mean, you do what you have, you take what you have. I mean, in 3 dimensions, as far as I know, there are the results by Balaban, but they don't actually construct the measure in the end. I don't think that there are, in some sense, many results. It's not completely clear what the tools are, but of course you would like to maybe try to construct the measure directly, but it doesn't seem to be, it seems to be harder if you want. But okay, it's not clear. Maybe there's another trick that one can come up with. The advantage, one advantage of stochastic quantization is that short time is a little bit like a perturbation parameter. Right? So in some sense, you have somehow time that gives you like a perturbative kind of parameter without having to, put like small constants inside your exponential.
Okay, thanks very much again. I think there are no more questions at the moment. Okay, good. And so we're right on time for the next talk. Okay, so join me again in thanking Martin and taking the late evening for the talk. And maybe I propose that we have just a few minutes break. So we'll resume it in about 3 minutes or so. Okay. Thank you very much again.
Okay. Okay. Bye-bye.
Bye.
Yeah, I try to share my screen.
Yeah, please, if you're able to. Yeah.
You can see my screen now.
Yes, yes, we can see it indeed.
Okay, so if I circle some words, you can.
Yep, we can see it.
Mm-hmm.
Good.
There's there's no delay. Okay. As I'm mirroring my iPad onto my laptop, I was worrying there's a delay. But okay.
Okay, yeah. Well, we can see it well on our end. Yeah. So it's a little bit the opposite for you, how it's early in the morning for you, right?
Oh, not very early.
Oh, okay.
10.
Okay. Yeah. I thought somehow it was a bit earlier.
Nicer if I give the talk in my office, but our building is under construction. A lot of.
Okay. Great. Okay, so let's continue with the second talk for today. So we're very happy to have Shen here from the University of Wisconsin-Madison, who will speak to us about the invariant measure and universality of the 2D Yang-Mills Langevin dynamic. Over to you, Hao.
Okay, thank you very much. Thanks a lot for the invite. My great pleasure to speak here. My talk is closely related to Martin's first talk. It's also about the Langevin dynamic, or in other words, the stochastic quantization of the Yang-Mills. But I'll focus on 2D. I won't say anything about 3D. And also, this talk will focus on issues such questions such like invariant measure and universality questions. So for convenience of the audience, I just again give a list of the references. So these are the 3 papers we recently finished. The first paper with AJ Chandra and Ilya Chererev and Martin Heyer, we consider the Yang-Mills measure, the Yang-Mills Langevin dynamic in 2D. So we construct this gauge covariant dynamic. And we also construct a state space. So on this state space, we have a notion of gauge transformations and Wilson loops and so on. And then so inside this space, we construct a gauge covariant dynamic for a short time. And in the second paper, we did this similar result in 3D. But there are several differences between 2D and 3D. For example, the state space in 2D is a linear space, but state space in 3D is a nonlinear space. But in 3D we also, so on this nonlinear state space, we also have a notion of gauge equivalence and so-called regularized Wilson loops. And in the last paper, in the third paper, which is the content of this talk, it's a more recent paper with Ilya Chererev, where we show that the Yang-Mills measure in 2D is actually indeed invariant measure for the 2D dynamic. And using this invariant measure, we also extend the solution of the dynamic to long time. And we also, so in this paper, we also consider so-called lattice Yang-Mills models, and we show that for various types of lattice Yang-Mills model, they converge to continuum limit, which is the continuum dynamic construct in the first paper. So those are the references, and since this new paper is strongly relied on it's built on top of the first paper. Let me just quickly review again the main result in the first paper, which Martin already discussed. So in this first paper with Chandra, Cheveref, and Hire, we prove this. So I just list all the results. So on 2D torus, we so first of all the first result is a deterministic construction of a state space called omega-1. This is space of the algebra G-value 1/4. It's a subspace of the classical Holder-Bessel space with a negative index, index alpha. So there are distributions, and on this space omega-1, we have a notion of gate transformations by Holder function G. And on this space, we can also define the so-called holonomies or Wilson loops. I'll define holonomy later, but for now, you can think of holonomy as a kind of non-abelian version of a non-abelian generalization of line integrals. So the difficulty of constructing the holonomies is integrating distribution, integrating very singular objects along curves. So what's important here is the Wilson loops are gauge invariant observables, and this means for so for this gauge transformation, right? So the Wilson loop observable for A and the Wilson loop observable for the transform field will be the same. So this gauge invariance for Wilson loop will be crucial later. And then we can take the quotient. So this space omega-1 quotient out the gauge transformations. This quotient is the metric space. And then we take the Yang-Mills test PDE. The Yang-Mills test PDE, which Martin alluded to. But we kind of write this in this talk. I'll write this equation in the shorthand form. So I just take off all the lead brackets and so on. So I just write the nonlinear terms like ADA and A cube, and this is the space-time line noise. We show that the equation is locally well-posed in the space omega-1. And here the C is the renormalization constant. So in some sense, this is really a family of equations parameterized by this constant C. And for each choice of the C, we can solve this equation in this space. So the solution, as you can see, is a distribution, right? So this space is embedded into space distributions. So the reason that we instead of solving the equation in the class space, the reason that we're not solving this equation in the classical space, but rather do this in the kind of new space we construct, is that for a generic distribution, we just don't have a notion of integral along curve, so we don't have a notion of Wilson loop. Okay, so now I'm going to write the solution as A of which depends on the C and the C. So just to specify which constant and which noise we're talking about later. And just to remind ourselves again that we obtain this solution by a kind of limit of modification. So we first modify the white noise by convolving with the modifier or something, and then take the limit. And then we show the so-called gauge covariance property, which says the following. So among this family of equations parameterized by C, there's a special choice of the C such that the following property is true. If we take two initial conditions which are gauge equivalent, A0 and A bar 0. And then we solve the equation starting from the two gauge equivalent initial conditions, and then we get solution AT and A bar T. And basically, we want to say that AT and A bar T are gauge equivalent in law for any T. So that's the that's the gauge covariance. But more precisely, what we actually prove is the following. So so we look at this solution AT with a modified noise Kc epsilon, and we also look at the solution A bar T starting from A bar 0 with modified noise. But before we modify this noise, we'll actually use the gauge transformation to rotate this Y noise. So what is this gauge transformation G? The G here satisfies a parabolic PDE, which is explicit by that. I don't want to write down explicitly here. So the only point is this PDE actually depends on A. And so we have this this equation for G, and then we apply this G onto AT, and what we show is that as epsilon go to 0, this gauge transform solution and the solution A bar with the rotated Y noise actually converge in probability to the same limit. Okay, that's the that's our statement. And since the rotation of space-time Y noise is still space-time Y noise in law, right? So rotation doesn't change the law of Gaussian. What we actually prove is that the gauge transform solution and the A bar with just the Y noise, in the limit, they have the same law. So this allow us to project. So this gauge property essentially says that we can project the solution onto the quotient space, and we obtain this process X on the quotient space. That's the final object we constructed in this paper, because eventually what we care is the Yang-Mills measure on the quotient space, right? So we get this process on the quotient space, and the Yang-Mills measure on the quotient space should be the invariant measure for this process X. So that's what we proved in this paper about the CCHS. And this talk about the paper with Ida Chavirev, we essentially lift this word expected. So we proved that the Yang-Mills measure in 2D is indeed the invariant measure for this process X. So I should first say a few words. What is the 2D Yang-Mills measure, right? What is that invariant measure? So the Yang-Mills measure in 2D turns out that has some special nice properties than higher dimensions. This was observed by physicists starting from the 70s. So there are nice properties such as the so-called invariance and the subdiffusion and so on. And there's also a long list of math papers. And so this is certainly an incomplete list. I apologize if I miss any important papers. But a common viewpoint in this literature that they view the two-dimensional Yang-Mills measure as a family of random polynomials. In other words, given any curve in the underlying two-dimensional space, you have a notion of polynomy or Wilson loop, and you just think of the two-dimensional Yang-Mills as a stochastic process taking value in Lie group, which is indexed by these curves. So in this paper, in some sense, like just in Martin's paper, we have a field A, right? But in this paper, in some sense, so they don't quite care about the field A. Well, in some sense, they do have a field A, but in the sense that one thought about the field as if you fix the so-called axial gauge, then the field is essentially a Gaussian field. But that's not good enough because somehow in the axial gauge, the regularity of the field would be below -1/2, which is too low. the right irregularity in two dimensions should be the same as the Gaussian-free field, which is slightly below 0. So in this more recent paper by Chererev, he actually constructed a field in the sense that under a very delicate gauge, which is not quite axial gauge, but kind of hybrid axial gauge with so-called Coulomb gauge. There is indeed a random variable taking value in that state space I mentioned, whose so there is such a field whose holonomies or whose marginals coincide with these papers. So that's what roughly speaking, that's what Ilya proved. Of course, modulo some technical conditions. And actually, this the omega-1 in Ilya's paper is slightly different from what I just said, but there is such a field. So what I'm going to talk about in this new paper with Ilya, right? So in this paper, we proved the following results. So I'll just first list all the results. So first of all, we prove a strong notion of uniqueness. If we go back to the to this statement, so we prove that there is a unique choice of the C such that this form of gauge covariance holds. But if you look at this statement again, well, the G here, the gauge transformation G here, plays a role of coupling between the A and A bar. And in particular, we have to use this particular G to rotate this Y noise. And after that, they convert to the same limit in probability. So in some sense, this is a very special coupling between A and A bar, right? So, well, of course, this is a kind of natural coupling, but in some sense, we only prove the uniqueness C such that the solutions are gauge covariant in a natural way, but it might happen that, right? So this statement doesn't rule out the possibility that you might have a different C such that AT and A bar T are still gauge equivalent, but they're coupled by some other way, right? So we show that the C is unique in the sense that the solutions are gauge covariant in the natural way, but we didn't prove the uniqueness of C such that the solutions are gauge covariant in any way, in some sense. And this is why we this is the new result. We actually prove a stronger notion of uniqueness. We prove that there is a unique choice of C, which will be denoted as C bar for the rest of the talk, such that once the initial conditions are gauge equivalent, then for positive T, they are gauge equivalent in law. Okay, so roughly speaking, how do we prove such result? So actually, we prove this result by using Wilson loops. Recall that I just said the Wilson loops are gauge invariant observables. So what we need to show is that if the C is not that C, the two solutions are not gauge equivalent. So how do we show that they are not gauge equivalent? Well, we show that we can take a certain special Wilson loop for A and A bar such that the Wilson loops are different. So since Wilson loops are gauge invariant, if the Wilson loops for A and A bar are different, then this means the A and A bar are not gauge equivalent. And of course, this is okay. This is a strong uniqueness is a result, of course, of independent interest, but it's also crucial for the next result. The next result, we did the following. So in physics literature, starting from the 70s, physicists like Wilson, Villain, and so on, they introduced a class of so-called lattice Yang-Mills models. And these are discrete Yang-Mills model define a lattice, and the discretizedness in the way such that the gauge invariance is preserved. Okay, so you have to discretize in a very, very delicate way to preserve the gauging environments of the model. So on the lattice, these models are well defined. So you can discuss all the properties and so on. You can study various results or do simulations. And so I'll precisely find these models in a minute. And what we show is that, of course, you want to show that as lattice spacing go to 0, they converge to continuum limit. This is what we show. So as the lattice spacing go to 0, we prove that. So we look at the dynamic, right? So again, you take the stochastic gradient flow for such lattice Yang-Mills models, and in the limit, this dynamic converges to the solution of our stochastic PDE. So this is solution A with a constant C and the Y noise C. So here we show that the lattice dynamics convert to A for some choice of the constant C. In principle, if you really want to calculate very carefully, in principle, maybe you can show that the constant is the same as that constant, right? As that unique constant C bar, but that would be extremely tedious if it's possible. So, so what we actually do is that we can actually use the strong uniqueness in the first result to show that this C is actually the C bar, the good constant for us to have the gauge covariance. The reason is that so we know that these lattice Yang-Mills models have gauge invariance, so their dynamics naturally have a gauge covariance property, and this passes the limit. So we know that the in the limit this limit must be gauge covariant. On the other hand, we in the first result we show that there's a unique C, which is a C bar, such that the dynamic is gauge covariant, and therefore the C must be the C bar. Okay, so this uniqueness of the gauge covariant dynamic in some sense help us to identify the limit of the discrete limit. And then we turn to the invariant measure. We show that there's a unique probability measure called mu Yang-Mills on the quotient space. So this is state space modulo of the gauge transformations. So moreover, this probability measure mu Yang-Mills is a unique invariant measure of the dynamic X. So this solved the problem I kind of alluded to earlier. So how do we show this? So roughly speaking, okay. So first of all, so according to the paper by Chavirev, we have a omega-1 valued field. So we just take the law of that field, project quotient space. So that gives us a measure. And how would we actually show this measure is the invariant measure for the dynamic? Here, we need to use something called the Borganski invariant measure argument. So so in this okay, so I'll explain the Borganski invariant measure argument if I have some time later. But in this argument, one has to okay, so it was introduced by Borgan for the study of dispersive PDEs. The start point is you kind of start with the finite dimensional approximation to the equation. In dispersive PDEs setting, usually they do some Fourier truncation, so you have finite many Fourier modes. And in finite dimension, you can explicitly check that the measure is the invariant measure for the finite dimensional dynamic. And then you try to have some uniform bound and pass the limit. And here we don't do the Fourier truncation. Instead, we take the lattice Yang-Mills dynamic, right? So on the lattice, the equation becomes finite dimensional, and on the lattice we can explicitly show that the measure is invariant, and then we use Born-Ganson argument to pass the limit. So so that's why our second result about the lattice approximation is actually crucial for this result. And then based on this result, another related idea of Born is that if you start your solution from the invariant measure, then you can actually extend the solution to any time, to long time. So that's what we prove here. So in the early paper with AJ, Ilya, and Martin, we construct this dynamic for short time, but now we can extend to long time. Actually, we can do this for any initial condition in the quotient space, not just the condition, not just the initial condition sample from the invariant measure, due to some nice ergodicity results by this group of people. And then so here we obtain the global WOWPS or the long time existence of the process based on some knowledge of the invariant measure, right? So another kind of open question would be really interesting to show is that whether you can construct global solution, the long time solution, without using any information of the invariant measure. That will be extremely interesting in 2D and 3D. So on the other hand, actually, we also have some results in the same paper where we can actually show some properties of the invariant measure using the dynamic. Okay, so so this is the next result, which is so-called universality of the Yang-Mills measure. What this means is that we look at the all the various type of lattice Yang-Mills models in 2D, right? So these are like the measures on the lattice, and then we take their continuum limit. What we show is that, okay, first of all, they have continuum limit, and then the continuum limit is actually the same, which is the mu ym. So in this sense, the mu ym, which is the unique invariant measure of the Yang-Mills dynamic, is actually universal. It's a universal limit of all the discrete Yang-Mills models. So the rough idea to prove this result is that okay. So first of all, we can prove some moment bounds for these lattice Yang-Mills models, and the moment bounds imply tightness. So we know at least we have some subsequential limit. But the question is how do we know that all the subsequent limits or the limits for different lattice Yang-Mills models are the same, right? Which is the mu ym. So how do we know that? To know that, actually we use the universality for the dynamic, which we showed here. Okay, so so we know that the lattice Yang-Mills measures are invariant measure for the lattice dynamic, and then we pass the limit, and the limiting measure is the invariant measure for the limiting dynamic. But we also know that limiting dynamic is unique by universality of the dynamic, and we know that the limiting dynamic has a unique invariant measure, and therefore the limit of all these lattice Yang-Mills models should be just that invariant measure. So so that's how we identify the limit. So this means that we have this nice characterization of this limiting measure, which is characterized by the unique invariant measure for the Langevin dynamic. And then so the last result contained in this paper is the following. So if you know something about two-dimensional quantum field theory, such as phi 4 or Liouville CFT, the field is absolutely continuous with respect to the Gaussian free field, and this is a really nice property. But this is not true for two-dimensional Yang-Mills. So instead, we can ask for the weaker property that is suppose we subtract the 2D Yang-Mills by Gaussian free field. What's the regularity remainder? Actually, we can show the remainder is almost C1. So this is so-called a gauge fix version of a gauge fix decomposition of the two-dimensional Yang-Mills field. So more precisely, we showed that we can find two fields called psi and B, where psi is just a Gaussian free field. Now, of course, the Gaussian free field also the algebra value one form, so the different components are independent Gaussian free field. And B is in C1 minus. Actually, not only that, we show that it has the moment bounds. So the C1 minus norm has the finite moment for OP. So we can find these two fields such that the sum of psi and B, if you project that to the quotient space, then that has the law, which is the mu ym. So how do we show that? We show that using the dynamic. Basically, the idea is the solution to the Yang-Mills SPD has such a decomposition, right? So we construct the solution to the Yang-Mills SPD using regular structures, and the byproduct of regular structure is it gives us a nice decomposition of the solution into a linear part, which is Gaussian, and a nonlinear part. So the invariant measure for the linear part is just Gaussian free field. So these are all the results. I just roughly explained the logic between all the results we showed in this paper. And maybe this is a good point to pause for, let's see if there's any question. If there's no question. Okay, so so we see that in this result, the lattice Yang-Mills model play a crucial role, right? So first of all, it's just very interesting to show that various lattice models they converge to the universal limit, both for the dynamic and also for the measure. And also the lattice approximation plays a crucial role for us to apply the so-called Borganski invariant measure argument, because we have to start with the finite dimensional approximation. So I need to tell you what is the lattice Yang-Mills dynamic. So this is the two-dimensional lattice. So it's defined the following way. I'm going to so for each edge xy, I'm going to assign a Lie group element called uxy. So you can think of the uxy as a kind of a unitary matrix, for example. So you have a unitary matrix on each edge, and then so basically our state space is the product of the Lie group over all the edges. And then on this space, we're going to define measure. The measure is a sort of Gibbs type measure. So it's an exponential of this action functional, right? It's just like what we did for the continuum Yang-Mills. We have an action functional, and then there's a product measure. And each of the duxy is a Haar measure on the Lie group. So basically, Haar measure is the analog of the Lebesgue measure for Euclidean space on the Lie group. So I need to explain what is this action function now. This is defined in the following way. Somehow I want the Lie group element on the different edges to be coupled, right? So what I do is I take a plaquette, which just means the 1 by 1 square. and multiply the Lie group element, the 4 Lie group elements along this along the boundary of this plaquette. Okay, so this is again a Lie group value element, and then I have this function S, which is a function defined on the Lie group, and the whole thing gave me a number. And then so I just sum over all the plaquettes, and that's my action function or energy of this configuration, if you want. So you can now on the lattice, it's actually much easier to check this model is gauge invariant. At least easier than the situation in continuum, because now the gauge invariance. Now the gauge invariance is defined the following way. So we take a Lie group value function called G, right? So G is defined on the vertices. And what we do is we kind of multiply the UXY from the left by GX, from the right by GY inverse. So in this action function now, you see that so UY is multiplied by GY inverse, and the UYZ is multiplied by GY on the left. So somehow the GY inverse and GY cancel here, and also GZ cancel, GW cancel. So in the end, we only have a GX and a GX inverse. But then if you assume that function S is invariant under computation, then this whole thing is just invariant under this gauge transformation. Okay, so this measure is actually invariant under this gauge transformation. So that's the lattice Yang-Mills models. And note that what's important here is this is a class of models, not just one model, because this S for the moment is arbitrary. Right? So depending on the particular purpose, the physicists define the different choices for S. For example, Wilson took the trace, and Whelan used the heat kernel. These are all natural functions satisfy this problem. So maybe it's helpful to so let's just compare the lattice Yang-Mills with the continuum Yang-Mills that Martin defined. So continuum Yang-Mills also defined by this action functional, where the functional is defined like the L2 of the so-called curvature. Right? So this is the curvature for the FA for the A, and apparently you might think the lattice model and the continuum model look quite different. In particular, one main difference is that the field A here take value in the algebra, whereas on the lattice the U take value in the Lie group. So that's the main result, main difference. So how do you kind of at least formally connect the two things? So the connection is the following. So you should think of the Lie group value field as exponential of epsilon, where epsilon is the lattice spacing. So exponential of the Lie algebra value, the Lie algebra value field. So you know, exponential Lie algebra element is going to give you a Lie group element. So on the lattice, if we take this plaquette product, then we get a product of the 4 exponentials. There's formula which tell you how to multiply this, which is to the leading order. This is equal to exponential of the sum. But remember that these A's are kind of matrices, like the algebra elements. So it's not quite equal to that. There are correction terms. So the correction term basically the brackets of these A's and sort of iterated brackets. Now you see we sort of see the structure in the continuum, because So the sum of the field is basically you kind of curl around the vector field along plaquette. That's essentially a curl of the vector field. And then the brackets, roughly speaking, correspond to this sort of brackets. Of course, there are also a lot of remainder terms here. So this discussion is kind of formal. It's also you can sort of see the discrete gauge transformation is really a discrete analog of the continuum one, because here we multiply the gx and gy, right? So xy are nearest neighbor vertices. So if you replace the gy by gx, then we kind of we will get this conjugate of a, but we create a derivative of g. So that's why we have a derivative term in the continuum. Okay, so you can see some sort of connection between lattice and continuum. But of course, the approximation on the classical level doesn't mean approximation on the quantum level or on the stochastic level, right? So we still need to show rigorously the convergence. So let's look at the dynamic, right? So we want to show the discrete dynamic convert to the continuum dynamic. The discrete dynamic again has this form, which is the gradient flow plus derivative Brownian motion. So here on the lattice, so on each edge, we associate a Lie group valued Brownian motion called B. We also have a kind of discrete analog of the Turk term, that's like Martin said. And it's possible to write down more explicitly this dynamic, but I'm not going to do that. So what we're going to do is that we want to show that when we pass the continuum, this dynamic convert to the solution to our SPD. The main difficulty is that, as I already said, in the continuum, the equation take value in the Lie algebra, but here take value in the Lie group. So how should we kind of deal with this issue? The strategy is the following. So I just mentioned that there's this exponential map, which maps the Lie algebra to the Lie group. Right, so the exponential of a should think of u as exponential of a, and here this dynamic is defined on the Lie group or product Lie group. So what we do is we want to use the exponential map to pull back the dynamic on the Lie group to create a dynamic on the Lie algebra. Okay, so and then so after that, we just need to work with the dynamic on the Lie algebra. So more precisely, what we need to pull back is okay. First of all, this function, right? This is the function on the Lie group. Okay, function is not hard to pull back, and then we also need to pull back a remaining metric on the Lie group. Why is that? Because you see here we have a gradient. So the definition notion gradient depends on the underlying metric, right? So in order to calculate the gradient of the pullback dynamic, we also need to pull back the remaining metric on the Lie group. And also we also need to pull back these terms. So so this kind of thing, calculation turns out to be quite lengthy. But after a lot of calculations and the rescaling, we sort of see a discrete equation taking value in the Lie algebra, which is roughly speaking written into the following form. Okay, so we still have the same sort of nonlinear. Okay, we have a kind of discrete Laplacian and the same sort of nonlinear terms. And then we have tons of remainders. And this is a discrete Y noise. So why do we have all these remainders? Okay, so first of all, we have remainders of the following form. So for example, we have a kind of new nonlinearity, but outside we multiply this epsilon. So you might think this term just vanish if the lattice spacing epsilon go to 0, but it's not, because the A here is very singular. So if you multiply something singular or something divergent with something vanishing, the limit is not necessarily 0. So actually, all these terms do have some sort of contribution in the limit. And we also, and I also just told you how to multiply exponential of so this sort of expansions, and we have some remainders. So this is the kind of BCH formula remainders. And then so it turns out that when we pull back the dynamic to the algebra, the noise. So initially the noise is additive, but after this pullback, the noise becomes modulated. So that's another source of the error term, remainder term. And then finally, as I said, we consider this large class of Yang-Mills models, right? We have this arbitrary function S in the Yang-Mills section, and we assume this function S. So we need to assume something for our universality class in some sense. So we assume that the function is given by the Lie group distance of this variable from the identity element of the group plus some remainder, and this remainder will also show up in the remainder. But in the end, what's very interesting is that we can prove that all the remainder terms, hundreds of them, convert to linear term, which is a constant times A. So different remainder term has different C, but so this C is kind of the sum of hundred of C's. So to summarize this, okay, so this is the main part, main technical part of the paper. But to summarize this into a theorem, we show that the continuum limit of the lattice dynamic is indeed this SPD solution to the SPD for some choice of the C. This C is the sum of all the little C's. So the proof of this, we use the discrete framework of regular structures by Dirk Gerhard and Manhai. So as I said in the beginning of the talk, we also want to identify this C. We also want to identify the solution as the unique gauge covariant solution, right? So we want to prove that the C here is actually equal to the nice C, which is called C bar. And for that, we don't really want to add up kind of hundreds of the constant C and compare with the C bar. We don't want to do that. We want to use the uniqueness of the C, the so-called strong uniqueness of the C for the gauge covariant dynamic. So for the next, I think I'm running on time, but for the next maybe 5 minutes, I'll tell you a little bit how we prove uniqueness of C for this dynamic. Okay, so recall that gauge covariance means that we start with two gauge equivalent initial conditions, A0 and B0. And we solve the equations from these initial conditions, and they are called A and B. And we want to show that if C is equal to that nice constant C bar, then the A and B are always gauge equivalent. But if C is not equal to that nice constant C bar, then they are not gauge equivalent. And as I said in the beginning, the idea is to use the Wilson loop. So I'm going to write WLA for the Wilson loop of A around the loop L. So I guess the precise definition of the Wilson loop doesn't quite matter. The only thing that matters is gauge invariant observable. So This means if C is at C bar, then the Wilson loop expectation for the AT and the Wilson loop expectation for the BT for any loop should be the same for positive. So basically, the difference is essentially 0. So this is because in the earlier paper we showed that with this choice of C, the AT and the BT are gauge equivalent, and also because the Wilson loop is gauge invariant observable. Okay, so the only reason that the right-hand side not 0, but something really small, like a small t to a huge power, is that you know, the existence time of AT and BT is random time. So after excitation, it's not quite a 0, but basically you can think of the left-hand side as essentially 0. And in this new paper, we show that if we don't choose that nice C bar, then we can find an example of initial conditions, like their gauge equivalent, an example of the loop L, such that the two Wilson loops are actually bounded from below by a strictly positive thing. In particular, they are not the same. Okay, so that's the uniqueness statement. So to prove this uniqueness, to prove this lower bound, it turns out that it's easier for the abelian case. So what does abelian mean? Abelian means the Lie group is U1, and in this case the equation becomes linear. Okay, just the heat equation plus this linear renormalization term. Maybe I have some little bit time to show you the abelian case. So in the abelian case, it turns out that nice constant C bar must be 0. Okay, so I can show you that if C is not 0, then the solutions are not gauge equivalent. So what we do is, as I said, we just need to find one example of initial condition. So what we do is we take the initial condition for B is 0. The initial condition for A is 2 pi I dx1. So the point is that so here it turns out that topology is really important. So we call the underlying space is the two-dimensional torus. So here the choice of the initial condition is a close one form but not exact, right? So this dx1 is well-defined one form on the torus, but x1 is not a well-defined function on torus. Okay, but these two initial conditions are actually gauge equivalent by this gauge transformation G. And again, this G is a well-defined U1 value function on the torus, but it's just this x1 is not a well-defined function on the torus, right? So, but if the unit torus, then because you know, if the unit torus, then this is still periodic function on the torus. So that's the okay. So we're using a topology, and since the equation here is linear, we can actually explicitly solve these equations using heat kernel and so on. So then we compare the two solutions, and only difference from the initial condition. Right? So the difference between them is this kind of evolution of the initial condition. And now what we want to show is the following. So if we don't take the 0 constant, then we want to say the Wilson loops for A and B are different, right? So in abelian case, the Wilson loop is very simple. I didn't define Wilson loop, but in abelian case, it's just the exponential of line integral of this one form. So how do we show they're not equal? Well, the difference or their ratio is going to be this, and we're going to show this not 1. So the difference between A and B is here, right? So this is why we have this term. Now, in order to show that this is not 1, we take a loop, which is just the loop that when you integrate this one form along that loop, it's equal to 1. in other words, the loop we should take is just the kind of this loop, which is the loop, the non-contractible loop that is winding around the torus. So the line integral of a0 is equal to 2 pi I. So now we see something interesting. So at t equal to 0, this is actually equal to 1 because the initial conditions actually take equivalent. But when t is a little bit positive, right? So when t is larger than 0, this is not equal to 1. So we really create a difference between the Wilson loops. So this sort of argument eventually we can extend to non-abelian case, but I'll skip the details. So the main idea is still to look at what happened for a short time. So basically, so now the equation becomes nonlinear, and what we do is we expand for a short time. So we kind of expand everything in T, and then we can see somehow the solutions A and B they differ by something linear in T, and eventually we can show that in non-abelian case the Wilson loops differ by terms like that. And then we can choose a special initial condition and a special loop such that this is non-zero. And this is how we create the difference, create kind of lower bound between the two Wilson loops.
There was just a question in the chat regarding the your previous slide. Is there any condition that these equations are parabolic? This relates to Martin's previous presentation.
Right. So right. So the discrete equations, we don't care. Of course, a discrete on a lattice, we don't care if they are parabolic or not. But when we want to take the continuum limit, we want the discrete equation to approximate the parabolic equation, right? So in Martin's talk, the gradient flow you start with is not quite a parabolic, and that's why we need to add the third term. And this also happened on the discrete level. So discrete equation, we also need to add a kind of discrete analog of the third term. So the discrete equation kind of approximate a parabolic continuum limit. All right, so I think this is the proof of the uniqueness. I think I really don't have time. So maybe I just skip the invariant measure argument. So as I mentioned in the very beginning, we can use the so-called Bourgain's invariant measure argument to show that the two-dimensional Yang-Mills measure is indeed a unique measure for our dynamic. And for this, we need to have some uniform moment bound to apply the Bourgain's argument. A key input is uniform moment bound for the discrete measures, and this is achieved by kind of strengthening early result by either Chadurev. Okay, so I just stop here. Sorry for running out of time.
Okay, thanks very much for the very nice talk. Okay, so as before, we have time for questions. There were already some questions during the talk. Are there?
There's a raised hand.
Yes.
Oh yes.
Do you hear me?
Yes.
Yes.
Hi. Thank you for the lecture. I have at least one or few questions. So mainly, I mean, I'm not really an expert on the Young-Mills, but nevertheless, you use Langevin dynamics. Could anything of this be put also outside of these dynamics in a different dynamic context? And also, as somebody who researches more on scaling limits, you naturally derived the limits that you've shown, but could they be interpreted in terms of the scaling limits you derive decomposition into GFF and another remainder? GFF is natural conformal object. Could this be studied? Are these scaling limits? And could anything of this make sense also in this context? Are there any scaling limits to derive for the processes that you study? Thanks.
Okay, so the first question is whether there are some sort of other versions of dynamics, right? So another important dynamic is a Hamilton dynamic. So it would give you a wave equation. So that will be actually much harder to deal with. But for simpler quantum field theory models, for example, so-called 5-4, there are some recent very nice paper. So for example, there's the long paper which show that the in 3 dimension the 5-4 measure is the invariant measure for the Hamilton dynamic for the wave equation. And also use the Bourgain's argument actually. Also this so-called parabolic stochastic quantization is not the only way of stochastic quantization. There's also something called elliptic quantization, where you well, it is some sort of a so-called Parisi-Soulas dimension reduction. It's kind of you can write down an elliptic stochastic PDE and study that. So your second question was
limits and the relationship to formal and scaling limits, or the limits that you have derived, can they be interpreted as scaling limits? Probably not for the parameters in the Young-Mills.
I guess the Gaussian free field. Yeah, I guess. Okay, so I think your question started from the kind of decomposition, right? So I mean, so for Gaussian free field, of course, there are various results about the scaling limits, Gaussian free field. I think, you know, some sort of, for example, some sort of random tiling or something. If you look at the bulk, then the kind of height function converts to height function is discrete, but in continuum limit, they convert to Gaussian free field. And also there's this whole list of Liouville CFT, which is essentially Gaussian free field, but penalized by the kind of entire area, the surface. So it's kind of random surface where the conformal factor, the random conformal factor is essentially by Gaussian free field. And that object is really very interesting. It's a scalar limit of many different discrete objects. So that's the examples I can think.
Thanks.
Okay, are there any other questions? Okay, if not, let's thank our second speaker, Shen, again. And the next one-hour probability seminar will be in 2 weeks from now with Theodor Sturm. as one of the speakers. Okay, thank you very much.
You're welcome.
All right, thanks.
You.
Bye.